Hey guys, so in this video, we would like to derive some relationship between F-divergence and total variation distance, some kind of a bound which can give us a clear picture of how these two vary. And we are students of IIT Madras. I'm Ram, and our friend Kishore is also presenting. And this is a part of our course project for the course Info Theory. So many of you will be familiar with something called scale divergence, which is basically defined as the divergence or distance between two probability distributions defined as same shape. Here we attempt to formulate a more general notion of divergence called F-divergence. It's defined as follows. F-divergence for two probability distributions P and Q defined on same measure mu is integral over the entire sample space Q f of P by Q d mu, where F here is a convex function with f of 1 equals 0 and F is defined from 0 to infinity to R. If you substitute f of t as minus log t, we observe that f divergence is basically KL divergence. An important remark here is that different functions can have the same divergence for all p and q. This is a very surprising result. Let's prove it. If for any arbitrary constant p element of R, we can formulate a function f of b t such that it's equal to f of t plus b into t minus 1 for all t greater than 0. The divergence with respect to f naught of p and q and the divergence with respect to fp of p and q will be the same. This is because when you integrate across the equation, you get the second term, which is the p t minus 1 term, as 0. So when you substitute t as p by q minus 1, since the integral p d mu equal to 1 for all probability distributions, you get a 0 there. So now we attempt to define another divergence measure called total variation distance. So if you substitute mod of t minus 1 in the definition of F divergence, you get the total variation distance. This can be viewed as the absolute error between two probability distributions in the sample space. Now let us try to view it in a totally different way. Now let's split the intervals such that the first part corresponds to the all x's such that p greater than q, and the second part corresponds to all x's such that q greater than p. Now, this is easily equivalent to suprema of p minus q, 2 into suprema of p minus q for that matter. So now we have another way of looking at this. It can be looked at as the maximum difference between the probabilities they assign on subset of the sample space. Now, let's define the perspective function f of f star of t, which is basically t into f of 1 by t. Since f is convex, f star is also convex. And also, it can be easily verified that f star of 1 equal to f of 1 equal to 0. Another easy fact to verify is that the divergence with respect to f for p and q is equal to divergence with respect to f star of q and p. Because by definition, f star of 0 equal to limit f star of t tends to 0, which is equal to limit q tends to infinity f of u by u. Now, Kishore will explain more about the ratios of total variation distance and f divergence.
Now we'll compute the ratio of f divergence to the total variation distance. If f is a function from 0 to infinity to the real line and is convex with f of 1 equal to 0, then we have supremum of df of p and q upon mod of p minus q equal to half of f of 0 plus f star of 0, where f star of 0 is the function defined in the previous slide, and supremum is taken over all probability measures p and q such that p is not equal to q. So for t in the range 0 to 1, we have f of t less than equal to 1 minus t f of 0 plus t f of 1. Note that we get this from Jensen's inequality, and because f is convex, we can use that inequality. F of t is less than equal to 1 minus t f of 0 because f of 1 is equal to 0. If t is greater than equal to 1, again by convexity of f star, we have f star of 1 by t less than equal to 1 minus 1 by t into f star of 0, since f star of 1 is equal to 0. Now stitching equations 1 and 2 together, we have f of t plus half f of 0 minus f star of 0 into t minus 1 less than equal to half f of 0 plus f star of 0 into mod of t minus 1. Note that we get this by combining the piecewise continuous function in the previous slide. So equation 3 reduces to equation 1 for t in the range 0 to 1, and equation 3 reduces to equation 2 for t greater than equal to 1. Observe that RHS of 3 is fb of t with b equal to half f of 0 minus f star of 0. Integrating both sides of 3 with respect to dq, we get dfd p and q equal to df of p and q less than equal to half of f of 0 plus f star of 0 into total variation of p and q.
So, since you have derived a relationship between total variation distance and F divergence, let us see where the supremum is achieved. So let us define two probability measures P epsilon and Q epsilon on a sample space consisting 0, 1, 2, such that P epsilon of 0 equal to Q epsilon of 1 equal to epsilon, and P epsilon of 1 equal to Q epsilon of 0 equal to epsilon square, and P epsilon of 2 equal to Q epsilon of 2 equal to 1 minus epsilon square. Here, epsilon tends from 0 to 1 by 2 into root of 5 minus 1 by 2. This is because your P of epsilon of 2, which corresponds to 1 minus epsilon square, should be between 0 and 1, and 1 by 2, the root of 5 minus 1 by 2, is the positive root of the equation. So now let us derive the bound. Limit epsilon tends to 0 between the F divergence and the total variation distance of P epsilon and Q epsilon, with the limit epsilon tends to 0, epsilon f of epsilon plus epsilon square f of 1 by epsilon by 2 epsilon into 1 minus epsilon with simple algebra, which corresponds to 1 by 2 into f naught plus 1 by 2 f star of 0. Now, a few points before we end. Total variation distance is very important for verifying the optimality of different tests like Fano's and Lekam's method, and appears in the measurement of difficulty of solving hypothesis testing problems. Some important inequalities you can derive from this include Pinsker inequality, which is the relation between KL divergence and total variation distance. So even though this whole derivation and the bound seems obscure, this can lead us to a lot of interesting insights in the end. Thank you for watching.